Welcome, everybody. We are so excited that you've taken time to join us today. We're Dr. Rusty Lowe and myself are members of the Globe Mission Mosquito and Globe Mosquito Habitat Mapper team. We had the honor this summer of working with some of the most exciting projects and students that a teacher has ever had a chance to work with. And today we'd like to share two of those projects with you. And so it's student research using Globe data. Turn it over to Dr. Lowe.
Hi, everyone. I'm Rusty Lowe, and I was really excited this year to work with the Earth System Explorer cohort of the NASA STEM Enhancement in Earth Science Summer High School Internship Program. That's a lot of words, right? But we were able to work this year with almost 50 students who were able to use NASA data, remote sensing data, citizen science data, and develop their own models in order to understand a question that they themselves identified as being an important research question. And so I just wanted to let people know that this program runs every year. And I believe that it's in February or late January or February when the applications are due, but there is a link right here. If you yourself are interested or you have students that might be interested in having an experience like the presenters that you're going to see today, we'd like to encourage you to look into this program because it really is amazing. It is very competitive, and you'll see that the work that they do is amazing. So that's really all I wanted to say today about this, but I really am looking forward to hearing the presentations, and I hope that you will have lots of questions to share with our presenters today. So without further ado, I think you're going to introduce the teams, Cassie.
I am, thank you. Our first team is Understanding Urban Heat Islands, and the student team will explain their insights into the factors contributing to urban heat islands and their implications for urban communities. They explored household income, greenery levels, impervious surfaces, and land surface temperatures to identify strategies for mitigating these heat-related challenges. As part of their research, they created a 5-minute video, which will play that summarizes their research. And then afterwards, we'll have comments from each of the kids that are here, explaining what role they had, their impact from the experience, any skills or knowledge that they came into or expanded during their internship, and any challenges or obstacles that they faced. This is a virtual internship. These students come from literally around the world, and they have had to navigate through different time zones. They've had to navigate any number of issues, finding the right platform to work with and talk to other people. And so we're extremely proud of their projects. And without further ado, I'll start with the first one. These are the patches that each of the teams made, and they'll explain those as they go. But each of the 11 projects we had created a different patch.
Hi everyone, we're working group 4 and I'm Abhiram Raju.
I'm Sophia Myers.
I'm Hubert Pye. I'm Noah Perales.
And I'm Anna Schiffman.
Over the past few weeks, we have worked on a research project, remote sensing correlations between income and land cover to analyze urban heat islands in Austin, Texas. Our goal with this research was to investigate what factors affect the formation of urban heat islands and how they correlate with each other. Through this, we hope to shed light on income land cover patterns to potentially assist future urban planning.
Every year, NASA sees interns choose an area of interest AOI of 37 points to classify based on land cover. We utilize the 14 AOIs in Austin, Texas from 2022 to 2024 and use the land cover data to investigate how factors such as impervious surfaces, which is concrete and asphalt, greenness, and median household income affect the formation of urban heat islands, UHIs, the phenomenon in which certain areas of a city experience extreme heat at a higher rate than others. We expected to find that as land surface temperature and percentage of impervious surfaces increase, greenness and median household income would decrease.
We derived our datasets from 3 different sources for this project. We obtained our percentages of greenness and impervious surfaces for each AOI from the Globe Observer database via Collect Earth Online, and we used the same to collect on-the-ground photos from each AOI to validate our land cover data. We use NASA Appears to request land surface temperature data, or LST data, for our AOIs from the EcoStress instrument on the International Space Station. Finally, we use the United States Census Bureau to find data sets showing the mean and median household incomes for the city of Austin.
Cross-checking land data with global observers help create variations in remote sensing data. This identification allows for local variations and for researchers to cover large areas and obtain more frequent updates.
We use k-means clustering and unsupervised machine learning model to classify UHIs in our study. To find the optimal number of clusters, we evaluated the silhouette score, Davis-Bouldin index, and Kalinske-Haribas index, which indicated that 2 clusters were the best fit. On the right, you can see the clustering result where each coordinate is grouped into high or low UHI risk. Our analysis showed that socioeconomically disadvantaged areas have higher risk of being UHIs. This is evident in the left graph, which compares the mean income values by risk level, showing that high-risk areas have lower median and average incomes. The right graph highlights the environmental factors, demonstrating that high-risk areas have less vegetation, more impervious surfaces, contributing to higher UHI risk.
We also carried out hierarchical clustering. The left plot here displays the results of the clustering analysis on our AOIs. Here, after calculating the same indexes for hierarchical clusters, the optimal number was 3 clusters. So 0, 1, and 2 represent high, low, and medium risk respectively. On the right, we've also generated pie plots for every variable to show the distributions and interactions between them. And over here, the top 2 graphs depict the continuous distribution of the entire data set, while the bottom 2 graphs display the bar charts for income and land cover cluster-wise. The high-risk cluster has low incomes and vegetation, but high impervious surface percentages. But the low-risk cluster, on the other hand, has high incomes and vegetation, but low impervious surface percentages. This shows how our clustering helped unravel trends in the data to identify areas at risk of becoming UHIs.
We also use dbScan because it handles noise and outliers well, which is especially useful when working with real-world data. As displayed, the clusters formed or differentiated within specific AOI points, unlike what we saw in k-means. In these clusters, we found that as income increased, so did vegetation, and in areas with lower income, there were, on average, more impervious surfaces. This is especially apparent in clusters 0 and 1, which follow the trend described previously. We hypothesized that UHI risk would increase with a higher percentage of impervious surfaces and decrease with increased greenness and median income. Regression analysis confirmed our hypothesis about the relationships. We found that there was a weak negative correlation with a p-value of 0.02 between impervious surfaces and income, and weak positive correlation with a p-value of 6 times 10 to the power of negative 18 between greenness and income. However, we want to note that once land surface temperatures were included, the data set was very incomplete. The clustering algorithms were not as effective in describing trends, and LST actually had very minimal correlations with the other variables, as it was relatively consistent throughout Austin. And thus, we want to strengthen our research in the future by expanding to California for a more diverse data set.
There are several potential sources of error in our project that may have affected our final correlations. The EcoStress instrument takes LST measurements at different times of day, so the timing for each data point was not consistent. 2 AOIs lacked impervious and greenness data, and some AOI points did not have corresponding ground photos on Globe Observer, preventing us from cross-checking them. Overall, our team members said that the NASA SEAS internship allowed us to enhance our skills, learn what a STEM career might look like in practice, and make meaningful connections with like-minded individuals. The unique challenges presented helps us grow as people and scientists, too.
We'd like to thank everyone who helped for the contributions. Please scan the QR codes to explore all the data sets and to view our detailed poster.
Please stop and ask if there's any questions from the participants. If you're comfortable, you can unmute and ask your question.
But I was just going to say that while people are thinking about questions, I would like to hear a little bit more about some of the things that you're doing. For instance, how did you decide on the technique? You used a very sophisticated technique in your analysis, and I would love to hear how you came up with the choice that you made, because it was obviously a good one.
Okay, I can try and answer this. So basically, from our data, we couldn't really use supervised models because we didn't have like an actual Y value to use. So instead, we did unsupervised models, and we just found a bunch. I was familiar with k-means clustering, so that's the type of analysis I did. I know Abraham did hierarchical clustering. So we all just took our strengths of the type of unsupervised learning we knew, because that is what worked best for our data, since there was not really a way to use supervised learning. in our situation.
That's a perfect answer. And we don't see any questions yet in the chat, so I'll ask another question about working with teams. One of the things that we really wanted to stress in this program was trying to promote that team science experience. We know from our folks that we work with at NASA that team science is something that a lot of scientists come into their research. When you do a doctoral dissertation, for instance, very often you're working off on your own project. Then you get a job, and then immediately you have to stop being in charge and you have to work with others. And so they're really excited about what we're doing here with teams. And I was wondering if one or two of you could talk a little bit about your team experience here and if it moved the bar for you in any way about how you think about your own research versus your research contributing to a whole. I'd love to hear that.
Yeah, I would love to start off answering this question because I think that personally for me, working in our team of 5 people really enhanced our research in such a significant way. In our case, I think that everybody in our team had completely different skills coming into this. So I know Anna had mentioned her previous experience with k-means clustering, and our teammate Hubert Pai and Abiram Raju both also had experience in coding. And I came in with experience in graphic design, and our teammate Noah Perales did as well. And so we had a really, really interesting mix of different skills. And I think that if any of this research was completed without the help of each other, it wouldn't have been able to reach the large scale that it did. And we also would have never been able to combine our skills in such a cohesive and significant way. Our unique backgrounds ended up coming together really well, I think. So if one of us wasn't very versed on a specific skill, the other one would, teach them certain aspects of it, or we would divide up the work so everybody had something to do that played to their specific skills. And it was a really awesome environment because I had never really worked in a team that was so comprehensive like that. But this was really my first experience working in a team science setting. And I would say that everyone on our team had such a unique background that it really enhanced our research. And I don't think we would have been able to go as far as we did with it had it not been for our specific team makeup.
Well, thank you, Sophia. That's actually really well stated. Catherine Myers has a question. She said, what are some of the lessons learned from actually doing this project? So I think she's probably talking more about the mechanics of doing it versus your outcomes. And Catherine, if I'm wrong, go ahead and clarify. But I'd love to hear about that.
I can talk about one of the lessons learned. So obviously you start off with one idea, and then as you go over the project, you might have to make some changes. That definitely happened with us because we were really thinking big for our final project, but with our 2-month internship, it wasn't fully possible, so we had to deviate a little bit. And in one instance is we actually tried using the land surface temperature, and we wanted to use that as our Y value to predict the data. But as it turned out, it didn't have a lot of correlation. So, like, one of the major lessons we learned is just, like, keep going with the flow. And if you need, make the changes needed because you'll still have some sort of impact at the end.
That's a really good point. I know that also from my own research, I had I had an idea starting out of what I wanted to do. And then it turns out that I have to make sure that the data that I could get fitted my question. And because it didn't completely address it well, rather than having a weaker project, I just simply changed my question to meet the goodness of fit for the data. And it sounds like you did that as well. So that's really impressive. And one person, AP, asked, what is the main goal or main idea of this project? And I think I can answer that basically the goal of the project was for the participants here to use their knowledge and their new skills to apply NASA data sets to the analysis of a problem that they care about. And so that was sort of the more general thing beyond their actual examination of urban heat islands. There's another great question here by Gensai that says, in general, what experience did this provide that sort of supported each individual's field of interest? Like, I know some of you came into this research experience just by how many people stated what their interests are. So many people came in wanting to do something with space and ended up, for instance, on an earth science team. So how did this experience meet whatever interests that you had?
Yeah, I mean, I can't speak for my teammates, but I will say that for me personally, I'm really interested in mathematics and data analysis, and I was really able to like get a first experience as to what a career in data analysis might look like. We did a lot of specific data extraction and filtering using tools like NASA Appears, a database online, to collect our data and then use a flagging system to filter out which data points were accurate and which ones not so much. And so I had never really handled data in that kind of way before, but there was a lot of trial and error that went into that process. And so, as somebody who's interested in data analysis, I will say that that was a really awesome skill for me to be able to try out. And I am by no means an expert. It was very experimental, but it made me realize like how much I love the subject. And then second of all, we use some softwares like ArcGIS that are really commonly used in the field, specifically in earth science, but also in other areas of earth and space science as well. So even if we go into a career outside of earth science, we've already had some practical experience with a lot of the commonly used tools there. So we won't be so taken aback, and we'll have something to go off of when we're exposed to these topics in a career setting for the first time.
Thanks. Does anyone else want to speak up before we move to the next group? Okay, go ahead, Cassie.
Let's just reiterate that this was a 2-month summer virtual internship that met for 1 day a week, literally, and the rest of the time was kind of an out of internship time that the kids put in on their own. Roughly about 150 extra hours of work they did during this internship. Some did a whole lot more, but you know, your interest in your skills. During the first part of the session, they were introduced to the science. We had outside speakers come in. They learned roughly the mechanics of how to go out and make their own observations, to look at data, and they were investigating probably 85% on their own recipe.
I'd say so, yeah. I would say probably more than that. And also, and we need to move on to the next group, but this also applies to both. You know, one of the things we wanted to do with this experience was have people actually collect field data, because as a scientist, and I know this is, you know, me as well, you know, you look at a data set and you just assume that those numbers are meaningful. But unless you've actually been in the field and collected that data, you know that there is a little bit of variability, there's a little bit uncertainty, and you have to learn to trust your data source. And I think that's a really important part of research, especially if you've never done fieldwork before. So we made sure that there was a fieldwork component in each one of these projects. So I think this was a really wonderful presentation, and hopefully we can get back to you, but I think maybe in interest of time, Cassie, we should move to the next team. Bravo, everyone. This was just magnificent. Are you guys going to the AGU to present this?
I think we're
Yes,
doing it
we
virtually
are.
to the AGU.
Awesome. So they'll be presenting this paper at the American Geophysical Union meeting. It is the biggest Earth and space science meeting in the world. And this year it's going to be in Washington, D.C. So we look forward to seeing your poster there. Okay, Cassie.
All right. Our next project is Agrivoltaic Farming for Performance Optimizations. The student research team members will explain their research study in analyzing the impact of solar arrays on surrounding vegetation in agrivoltaic farming. And they'll share how this approach can enhance agricultural yields while promoting renewable energy.
Hello, our names are Yuki Chen, Ethan Poon, Eric Middleman, Michael Manders, Enya Perales, Arjun Nair, and Joanne Miranda, and we are the Agrivol team as a part of Earth Systems Explorers. Our project is analyzing the impact of solar arrays on surrounding vegetation in agrivoltaic farming for optimization of performance. Agrivoltaics, also known as low-impact solar, is a practice of using the same land for both agriculture and solar energy production. It offers an alternative to the complete conversion of agricultural land to solar locations. This co-location practice has the potential to both address energy inequity by supplying solar energy in locations less centered on the electricity grid, while also helping farmers diversify income through land lease payments and other business models. Agrivoltaics can sustain rural farming economies, which have an especially growing need for support. Further, only 2% of large solar array projects in the US are agrivoltaic, highlighting the potential for growth of this practice.
The success of agrivoltaics relies on optimizing the balance between energy production and agricultural output. Solar panels can create microclimates which can significantly affect plant growth. Our research question is, by using remote sensing tools and satellite data, is it possible to analyze the impact of solar arrays on surrounding vegetation health in order to inform and facilitate the future and success of agrivoltaic projects?
We approached this question by outlining the data of interest. Our first step was identifying agrivoltaic solar projects in the US. We first sorted through the Globe Observer AOI points to identify areas with solar panels and overlaid them with the US Solar Photovoltaic Database and filtered to find agrivoltaic projects. After identifying these specific locations on the US PVDB, we matched them up with data on the Landsat database. By inputting the location into the Landsat Time Observer, we were able to identify locations of interest and extract the data.
We then decided to use the NDVI, spectral wavelengths, and TCG data from the Landsat satellite to identify any trends occurring after the installation of the solar array. The NVDI estimates the amount and health of vegetation on the land. Band 4 shows the total red wavelengths. Less reflected red light means more photosynthesis takes place. The TCG shows photosynthetically active vegetation. We use the Landsat time series to allow us to access and download the data surrounding the specific agrivoltaic solar farm. After downloading the CSV files, it is then separated by measurement type. Then a Python program is run on the collection of CSV files to combine their data. The program starts by parsing the raw data from the CSV file. Then, using the construction year from the metadata, it takes a snapshot from 15 years prior to the construction to up to 10 years post the construction. It then centers this data around the construction year. Then it averages the data from all the measurements and outputs that to be graphed in Excel.
The NDVI data showed a decrease of 18.5% after the installation of the solar panels, indicating that vegetation health decreases with the implementation of agrivoltaics. Data show that band 4 decreases by 40.6% after the installation of solar panels, indicating that photosynthesis increased after the implementation of agrivoltaics. This can likely be attributed to the increase of red light absorption from the solar panels.
Data showed that TCG decreased by 54.2% after the installation of solar panels, indicating that photosynthesis decreased after implementation of agrivoltaics, signaling possible vegetation health decrease.
The decrease in NDVI and TCG suggests a decline in the overall vegetation health and photosynthetic activity following the installation of solar panels. However, decrease in band 4 suggests increased energy use under the conditions created by the agrivoltaic arrays. This research shows the complex interactions between solar arrays and surrounding vegetation and will aid farmers and energy producers by contributing to the sustainable growth of agrivoltaics. We expect to create an application interface to predict solar power potential or solar exposure in an area. Our tool will further optimize best land usage for efficiency in energy and vegetation growth. We also want to explore variation in agrivoltaic farms and attribute changes to conditions such as sun angle, panel area, location, along with relevance to its weather. Determining what factors can influence values like B4 and NDVI can be essential for future research.
The best feature of the SEAS internship was that we were able to pursue our own projects based on our own interests, which allowed us to work on what we were passionate about. The main challenge that we experienced was trying to fit our research goals into a short time frame that we had.
Overall, we all reflect that the SEAS program both gave us insight into different fields of earth science and provided us with mentors that allowed us to explore our passions deeper.
We would like to thank our SEAS ESE mentors Rusty Lowe, Cassie Sofing, Peter Nelson, and Andrew Clark, and the NASA SEAS program for providing us this opportunity to conduct research through this program. Thank you.
Thank you.
Wonderful. If anybody has any questions, you can either just raise your hand or type it in the chat. When you were doing this project, I didn't know too much about this topic, but since that time, I have a colleague of mine who lives on a ranch, and they right now are trying to evaluate the potential of doing agrivoltaics on their ranch. They raise cows, and what would be the impact of having a large solar array on their rangeland. So just not looking at your graphs or anything, what if I was going to give him some advice based on what your research was, what would you suggest?
The largest things that we saw from the data was that the solar panels truly do take away from the solar energy that's reaching the vegetation. So that was one of the biggest things that we saw in the data after the solar panels were implemented, that the vegetation wasn't reflecting as much light as we wanted them to. So obviously that affects the health of them. So we would recommend some sort of tracking system with the solar panel system so that there is a balance between what sunlight is hitting the solar panel and what sunlight is hitting the vegetation. So that was one of those things that we had tried to pursue or try to understand after the internship. We were trying to see what kind of system and balance could be made from those differences. But my recommendation would be that we have to definitely look at how we can have that balance between the light from the solar panels and light for the crops, and how much is really necessary to maximize both. So some sort of tracking system where the solar panel can move, or some sort of arrangement where the sunlight can hit both at the maximum level, is definitely the most crucial aspect in that, because our data showed that the light access to the vegetation was the most important factor in deciding how successful the system would be.
That's a really great answer. Thank you for that. We have a question here about how did you come up with your project? What kind of, who had some experience with solar panels or had interest in solar energy? And we're just really curious how you came up with this idea.
Yes, I think my partner is having some technical issues right now.
That's okay.
But
Yeah.
if I had to answer, definitely when we were first trying to figure out what topic to do, we considered the different interests of everybody. I think that was one of the highlights that we experienced in the Earth Systems Explorer team, because we had so much liberty in choosing what topic we wanted to go to. So me personally, I'm very interested in like energy equity and renewable energy. And in our team, we also had a few people who were interested in vegetation health. So we thought, is there an intersection between those two things? And we had talked to our mentors like Peter and our peer mentors, and we thought about where is that intersection, where is that combination, and we ultimately settled on, well, what do solar panels have effects on in like surrounding vegetation? Because we think about how they affect temperatures or their microclimates, or how they're really utilized in the rural areas that they're mainly in. So really, I think it was the combination of all of our passions, and it kind of settled perfectly into that kind of agrivoltaic topic. So I think it was a really kind of like a luck type thing that we were able to find the intersection between our passions that were also like not as explored in the scientific community, and something that we knew could have a real life world impact on our real life world impact with our research. So I think this topic was just something that aligned perfectly with what we were interested in as a team.
That's a really good
Yeah,
answer. Oh, are you there?
Yeah, I'm here. I can also attest to that. I really agree with that, especially since I'm also interested in like electronics. So I was thinking, oh, how can we look at electronics, especially in relation to energy equity? And I guess that whole, case with vegetation and analyzing that. So I felt that it also just fit perfectly with my interests as well, being interested in electronics and like seeing its applications for vegetation and energy equity.
Really good. And with this question about how do you come up with a project, I mean, I think you gave a really good example that people came in with their own interests and their own skills, but almost nobody in our group was an Earth system scientist or had that as their area of specialization coming in. Lots of people had a little bit of coding experience. Lots of people had interest in energy or ecology or the environment or space, right? But, bringing those all together, the one thing that the requirement of all the projects was that the individuals needed to be able to use remote sensing data and citizen science data in their projects. So that's a pretty small amount of, what do I say, of requirements. The requirement was relatively small, and it really kind of opened up the entire world of experiences and research that could be done. I wanted to also ask you guys while we're here, how about that team experience? I think there are only 2 of you here today, but I'd love to hear about how the team experience was for you.
So we did have some difficulties, I think, navigating communication with all of our members, especially because we are not face to face. And because we have those once a week meetings, we did have some struggles with trying to kind of delegate our tasks to every single team member, as well as kind of getting that contribution back. In terms of, we had some miscommunications there. However, because I think we're all very passionate scientists who really had the common goal of trying to find this answer, trying to further this research, ultimately, even though we had to go, although we had to like cross some barriers, we were able to finally get that final project done and get everybody's input and everybody participating in their own way on the project. So I think that was a valuable lesson that I learned through this internship, was that there are going to be some challenges that we'll face working as a team and figuring things out and getting everyone to contribute to their roles and making sure that everybody is understood and the challenges and what they want to contribute and how that dynamic works as a team. So I think that was very valuable in itself, that I was able to learn that, especially in a virtual environment where how that's going to be a large component of our human to human interaction in the future as humanity moves to more virtual types of environments. So I think that was something that I learned a lot from.
Excellent. That's a really good answer. That's a really good answer. Are there other questions that people have about this team and the work that they did?
Yuki, did you and Ethan have a message that you wanted to put out there, or did your questions, or did we already get that out of by asking it other ways?
Yeah, I think the questions really covered what we wanted to say.
Okay. I do have another question though, and it's about, like, we do have some people that are going to be viewing this or are viewing this that are considering applying for a SEAS internship. And what do you think was the most important preparation that you brought to this program before you actually became part of the program? Like, why do you think you were so successful? Actually, anybody could answer this one.
Sure, yeah, I can talk a little bit about this. I think one thing that really helped me was just generally being, I guess, curious and wanting to learn more and accepting to what other people had to say. I mean, me personally, I'm very interested in electronics and I guess like the technology aspect. So I think that I kind of brought that kind of expertise to this. Like Yuki said, she's very involved with energy equity, and I guess just learning from all of my teammates, being very open to the ideas, to different projects, I guess, different perspectives, I think really helped me to, I guess, make the most of my SEAS experience and produce such a successful project.
Great answer. Would anyone else like to answer that question?
I definitely agree with Ethan with saying that because we had such specific passions that we brought to our team, we were able to pursue our projects very actively and have common goals. And also, I think that my experience with leading teams with that passion was also very contributing to my application process as well as this team, because that ability to kind of see our common goal and have like empathetic leadership and see what all of our teammates' passions are and what they want to contribute to the team, and understanding that was definitely a really integral part in this internship, because definitely navigating the teamwork aspect over this virtual environment was one of the biggest aspects of figuring this internship out and the success of our project.
Thank you. Anyone else?
I can add, if you're passionate about anything, you should, like anything STEM related, you should apply. There will be a place for you. I'm also one of the people who's really involved and really loves astronomy and space, but I also really enjoyed this internship, even though it was about earth science, because I was able to delve deep into a different type of aspect. And like, if you're just like Yuki said, just curious and like you want to just learn more, like this is the place for you, because you will find it something how you can apply your passions into the specific groups. And I also had a lot of leadership experience, which definitely helped with communication and just working with the group.
Excellent.
So Sophia or Ebram, are you?
Yeah, absolutely. I think that Anna and Ethan and Yuki touched on some really important pieces, especially what Anna said about finding something that you're passionate about in a STEM career. Because, like she said, no matter what your project ends up entailing, there will be a place for you to show your own skills in the project. I definitely think that before the internship, it's good to know just like if there are any specific areas in earth science or space science or anywhere in any kind of STEM field that you're just really passionate about, do a little bit of research, find out what it is about that topic that interests you so much, and prepare to do more of a deep dive on it, because honestly, I think that this internship covered so many broad topics under the umbrella of earth science. You could have taken it in infinitely many directions. And
That's
if
true.
you come into
Yeah.
the internship with an idea of a topic or a subject that you really, really want to focus on, hold on to that and bring it up to your team when it's time, because I guarantee you there will be an application for it.
Well stated. Thank you.
Just to add on as well, I felt like honestly over the entire internship, everyone comes with such a diverse perspective in especially ideating how to go about solving a problem in different ways. And since there's no one right answer, since you're getting like we're meeting people from all over the world, you get these different perspectives that can really enrich the entire internship. So I would just say, just be completely open in every thought you have. Just put everything out there, and there will be a place for every idea, like Sophia said. And I think one more thing that I really learned over this entire internship is how to deal with like challenges, and when something you're trying to do doesn't work out. I think that teaches you a lot for the future as well, and how to go about these research experiences or for the work atmosphere as well. So I think this internship really prepared me to do that, and I really recommend everyone else to also apply for this really enriching experience.
Well
Are so
stated.
much so wise beyond your years. I don't
I
think when I was a junior in high school that I was even thinking about this. But kudos to you all for your leadership skills, your enthusiasm, and your quest for knowledge. So you're taking the right steps for the future.
Mhm. And Yuki, is your team going to be presenting at the AGU your poster?
Yes, we are virtually.
Wonderful. Wonderful. I look forward to seeing it. Yeah.
Well, I have one last slide to share before we wrap up our discussion tonight, and that's a series of globe data and IVSS focused webinars that the science activation teams, and that includes many NASA science projects that Dr. Lowe and I work with. There's 2 different sessions. There's 2 different series of talks during each of those, so you won't see the same thing if you show up twice. And it's October 24th at 7 p.m. Eastern time. And there's the bit.ly there to register. And then October 28th at 7 p.m. Eastern, we've got air quality, clouds, eclipses, snow, ice, the urban heat island effect, vegetation, including trees and methanology and land cover campaigns, and then water with mosquito habitats. There are also other data sources that would be included. So if you're an educator looking to try to find an area for your kids to get into, the projects are open for submission January 5th.
And the International Virtual Science Symposium is open to students of all ages from elementary school through university. So there are different, there are different levels of competition, but we really have seen some wonderful science come through this symposium in recent years. So, and I believe that both the teams today are going to have their submission in the IVSS. So thank you also for that as well. It gives you another place that you're able to share your science and make a difference.
All right. And if there's any further questions with your registration, I think you got my email address, but I'll put it in the chat just in case. Feel free to reach out to me and I can pass along your question to the right parties. So with that, I thank you all very much, and I thank you for sharing your Thursday evening with us kids, and one more day of the week. make it through.
Well, thank you for organizing this, Cassie. It was really exciting to hear your projects presented again and having the chance to ask a few more questions than we were able to ask at the symposium last August. So August. So thank you a lot.
Again, thank you all for coming, and we'll see you next time.
Okay.
Thank you for having us. It was an honor.
Yes, thank you so much.
Thank you.
It's our honor. Thank you.